About what is a waveform. With sound, you have something, some type of physical body that creates a vibration. And just like a rock being dropped into a puddle, when you make that vibration, you see waves traveling outward from the vibration. So here's the rock that we just dropped in the puddle, and these guys are the waves. Now, you've probably seen something like this before, and it's not unusual to think of sound in these terms. But if we took this and tipped it to a different plane so that we were looking at it, instead of straight down, we were looking at it vertically from the side, you would see these waves looking something like this. And that right there is one cycle of a vibration. You've got your positive, which is the part that comes up. You've got your negative, which is the part that comes down. And this basically is a 360-degree cycle from point to point. So your waveform is a vibration traveling through the air most of the time. For us, when we're listening over speakers or when we're listening to a live concert, we're listening to vibrations being created from the instrument, a brass instrument, or the wood of an acoustic guitar. That top of the guitar is vibrating, and it sets the air in motion, and we hear that just as we would anything that we don't even think about just because it's such a normal occurrence. But as sound engineers, some of this stuff needs to be in the back of your mind a little bit because it's going to be applicable when you're trying to make decisions in the recording process. So one thing that every sound wave has is what we call amplitude. And that is the distance above and below the center line. The amplitude would be the distance from here to here. And even though it's not perfectly correct to describe amplitude as loudness or volume, psychoacoustically speaking, that's kind of what it is. The amplitude is the intensity, and the intensity can be measured by the distance off the center line. So we can think of amplitude, I'm going to put it in quotes, as loudness, even though amplitude technically is not measured by decibels. That's sound pressure. Not a big deal for us, but something to tuck away in the back of your mind. If this waveform had a higher amplitude, it would be a more intense, louder sound. However, we haven't changed anything else. The distance from here to here is still the same. All that we've changed is amplitude. Okay, our next point here, every waveform has a frequency. I'm going to draw the wave again here. And at this point, we're not talking about the distance from here to here. We are talking about the distance from here to here. So frequency is the rate at which the vibration occurs, or cycles. As you make it faster and faster, for instance, something like that, or it doesn't have to be smaller, it could be like that. As this time gets shorter and shorter, the frequency gets higher and higher. So obviously something like this might be, whereas a shorter frequency would be, and that's just something that we can measure, by the way, in hertz. So we actually put a number on it. This right here, we might say that this could be 200 hertz, which is in the ballpark of middle C. Middle C on the piano keyboard is in the ballpark of 200 hertz. Not perfectly, but it's close, maybe 230. Whereas something like this might be more in the ballpark of 5,000 hertz, which I could write 5,000 Hz, or 5 kHz for kilohertz. So again, frequency, and this is going to be something that we spend a lot of time talking about, because this is the whole idea of EQ, equalization, making things brighter, making things duller, making the bass stronger. These are things that we can play with as far as cranking up the amplitude of certain frequencies to change the way that our music sounds. Another thing that every waveform has in common is a fundamental. The fundamental is the lowest resonating frequency of the vibration. So it's the primary tone, the primary sound. Some sounds, like a sine wave, have nothing happening but the fundamental, and it has a very artificial synthesizer type of sound, almost just like a pure but not natural kind of drone hum. That's a case where if you're looking at a frequency spectrum, for instance, if I have a meter pulled up that shows me frequencies, this would be down here really low at 20 hertz. Up here would be 20 kilohertz. I might see a fundamental that looks like this. And that's the only peak that I would see on my scope with a sine wave. But with anything else, like an actual acoustic instrument, a piano or a guitar or whatever, you don't just have the fundamental. You also have, put it down here, number 4, harmonics. And these things are additional frequencies that help give sound its character. So you wouldn't just see this one big spike if you had a guitar playing through, and we're going to do this in class so that you can see it. But when you play one note, just one note of a sine wave, it looks like that. One note on a piano is going to look the same note, by the way. One note on a piano is going to look crazy. It's going to look like that because it's got all these extra harmonics that are giving the sound its character. So these are things, by the way, that we can also manipulate as recording engineers in order to help bring a sound out. That's a trick we'll talk about another time. One of the other things that every wave has is velocity. And this is pretty simple. For most of us, when we're sitting in a room, let's say it's 70 degrees, nice and comfy, then sound travels at 1,130 feet per second. Doesn't matter what the frequency is, doesn't matter what the amplitude is, the speed of sound is the same. And this seems like something that's not going to be a big problem because most of us plan on recording things fairly close. However, it can actually rear its head, and we're going to see how that happens with the next point, actually. Phase. Every waveform has a phase to it. The best way to understand phase is really when you talk about the same sound being picked up by two different microphones. So let's do a little illustration here. Let's say that I have a snare drum. All right. And maybe I've got a microphone over here. And then I've got a microphone over here. We'll put a bass drum off to the side here. Now I've got a microphone over here for the bass drum. So clearly, here's my little beater, pow. So clearly, I'm trying to get kind of an overhead recording with this one to kind of get the whole drum kit, whereas this mic is close on the kick drum. Now, the thing is, because sound travels at a constant rate, when you hit this snare, the distance from this snare to this mic and from the same snare to this mic, it's different times. So you're actually going to have the snare sound slightly out of phase in these two mics. It's the exact same sound, but what's happening is the first mic is, let's say, catching it right here, and the second mic isn't catching it until it gets to right here. And now, both of those, even though the second one is not as loud probably, because it's further away, these things are still being put together. They're being combined. And so you end up with these two sounds fighting each other a little bit as they are not perfectly lined up. This changes the frequency, the actual sound, the character of the snare drum. Now it's possible that it could make it even better, but it's more likely that it's going to mess things up. And a lot of times, if you've got a whole bunch of mics, like all over the drum kit, then drums are often plagued by phase problems because you've got all kinds of mics trying to get just this one sound really punchy, and yet you've got bleed from all the other elements of the drum kit getting into each other, and this bad phase stuff happening. So that's something to realize, remember, and we'll also be dealing with that with various techniques in the future as well. Okay, and finally, the last thing that every waveform has is an envelope. The envelope has to do with the attack, the sustain, and the decay. The best way to describe it is just to kind of draw you a couple of different envelopes. Let's again talk about a snare drum. A snare drum is going to have a very strong attack. So as we're looking at the waveform, we might see a very strong peak followed by a very rapid decay. So there's your crack, and then it's gone. Whereas an electric guitar, if you're going to pick an open note, doo, then your waveform may very well look like that. So your envelope is this whole thing. It talks about the attack, the sustain, which is more obvious here, and finally the decay, which is this last little bit. All of these things are things that we can alter or make small changes to, both before we record, as we're recording, as we're printing to tape, and after when we're mixing. For instance, you might want to increase the attack of the snare. If you want to do that, there are ways to actually boost that attack while not changing the rest of it. Or maybe you want to fatten up the snare. So there are ways to reduce the attack here and then bring the rest of this up volume-wise. But that's the type of thing we're talking about when we say